system design. So before I go ahead, so essentially this module, this today's session is broken into three parts. Part one, introduction to digital system. Part two, digital system design process, and part three, introduction to hardware description language. So what we can do is I can have a 5 minutes or 10 minutes break after each part, so I can take up your questions and then we can move to the second part. So all of these three parts are kind of independent to each other. Yes, so let's start. So you see the module name is design of digital system. So first we have to understand what is a digital system, or in fact we have to first question ourselves that what is a system. So you see the system word is allocated to many things, like when we start reading science, we say solar system, we say computer system, we say family system. So the system is a keyword where we say that it's a kind of a closed entity where things inside the system, they are interconnected to each other, while they interact with outside entities of the system with a very defined interaction levels. Okay, so here the system is a digital system, very specific. So digital system means the system which will take digital inputs and which will take out digital outputs. So basically a system which has digital inputs and digital output would be a digital system. Of course, it would be inside a digital system, it would be doing some digital transformations. Okay, so I can make this digital system like this, that it has a digital input, and inside there would be, right now it's a black box or a blue box, and it would be giving out digital outputs. What is a digital input or a digital output? Digital, anything which is quantized, or basically which is sort of an integer, which is quantized, that we can call a digital input. Okay, so now what kind of applications do we see? Which take digital input, digital output. So you can see that if we look around us, then we can see that, for example, our mobile phone is a digital system. Your laptop, your computer, all the computing devices essentially would be a digital system. And then if we go beyond, then as the topic of this workshop, IoT, most of this IoT, there would be substantial digital system there. Embedded systems, many of these embedded systems, they're all substantial part is a digital system. So now you can even go beyond. For example, in most of the automotives or most of the advanced cars, there would be thousands of microprocessors and thousands of digital systems inside there. So for example, when you say power brake, when you say power window, whenever you say that it has a automatic, anything automatic in your car would have some automation component, or essentially some digital system associated with that. Okay, so in the communication words, so whenever we communicate, whenever we pass a message through a mobile phone, then these are all right now, like most of the time, these are now digital systems. So that means when you pass your message, then your modem will come, your communication channel will come. So most of these things are now digital systems. So that way, these digital systems are more or less part of our life, and they're there in each spheres of our life. But before moving ahead, there is one question that comes in our mind, that when we say digital system, input is a digital, output is also digital, and digital means it's quantized both in time as well as in value. Okay, but in real world, there is no digital. See, when we see, our eyes will look as all the information, whatever eyes see, they're all analog in nature. That means they're continuous in space, continuous in time, continuous in their values also. Similarly, when we speak, so all these all these voice vibrations, they're also analog in nature. That means they're continuous in time as well as continuous in values. Okay, so in other words, what we can say is our word we see or senses we have or whatever data we interpret, they're mostly analog in nature, but still we are talking about digital systems. So how things are done, actually most of our system, that's why I said in IoT system or in embedded system, substantial portion is digital system, because there is some analog component also involved. All the embedded systems, they would be talking to some real life things. So they will take analog input. So for example, speech would be taken as an analog input. Then after that, it would be sampled. Sampled means it would be sampled in time, as well as after that sampling of time, it would be quantized. So that means that value would be quantized. Okay. So it would be quantized. Now I used to say quantized in time as well as quantized in space, quantized in value. So this analog input is now quantized using analog to digital converters, and these analog to digital converter will give out a digital input, digital output that would be given as a digital input to digital system. Similarly, your digital system will finally work out as an output. So for example, whatever in screen you see, so the output was given as a digital output, but after that there was a digital to analog converter, and based on that, brightness of each pixel is set. So final output would be analog output. So this is the overall system. Then where input actually is analog, but it is converted to digital, and finally we have to focus on digital system. Then the next question which comes to our mind is then, if actual input is analog, actual output is analog, why we are creating a digital system? So answer to that question is, digital system offers many advantages. It is accurate. Accurate essentially means that whatever input you give, always it will produce the same output, same level of accuracy. While in analog, for example, you can do multiplication in analog as well as multiplication in digital. Digital multiplication will always give the same result. We can also call it reproducibility. But your analog multiplication, because of your temperature variations, because of your mobility of carrier variations or process variations, there can be certain changes in the output. Similarly, this digital system, because of advancement in last 50 years of research and development, they are programmable, they are maintainable. Programmable means that we can change the design. We can change how those inputs need to be processed. So essentially, all your processors are digital systems, and all the processors are programmable. So that means I can write whatever program I want to write in my processor. That's how these digital system would be programmable, and we can write any kind of processing. They can be maintainable, and design automation is also an important part, because we can make any level of complexity in the digital system. On the other hand, if I want to do the same thing in analog, design complexity is very high. We are still not able to achieve any kind of not major achievements in the automation of analog system. We still have to work transistor by transistor. Okay, so disadvantage would be definitely area, power, and performance. So for example, the same multiplication that can be done in an analog system in couple of nanoseconds, that would take hundreds of nanoseconds in digital system. So there would be an order of 100 times more cost, 100 times more area. But because they are reliable, because there is less possibility of error, because they are programmable, that's why we would like to use digital system. Okay, so with this background, this I have already covered. So with this background, now let's answer one more question. That so digital system is also looks like a future, because the growth is kind of an exponential. So all of you have heard of this Moore's law, where we say that transistors are doubling every 16 months or 18 months, sometime 24 months. So because transistors are increasing, doubling every 18 months, so number of transistors are increasing. So because number of transistors are increasing, what is the advantage? Now we have a lot of processing. All the transistors are cheap, so we can do a lot of things. So because, and why these transistors are increasing? Because essentially because of technology. Technology, now the scaling, the transistor node or fabrication technology is getting advanced every 18 months. That's why when we are in a new technology node, we can compact more number of transistors in the same area. And on the other hand, this is also a kind of an economic law. So we would, because of marketing and because of other economic landscape, you see that all the mobile companies or computing companies, they're pushing that you have to discard your mobile phone after 3 years, because new mobile phone is coming with new features, with more powerful processors, with less power and all those things. So because of that, compute requirement will also increase, and this increases one, because of our applications have become more and more complex. Second, because of economics and marketing, that people are pushing that let's have more complex systems and more complex applications. Okay, and all of those things is also possible because we can automate the design. Automate the design means that right now in one chip, so if you see here, 2020, around 1 billion transistors are there. So 1 billion transistors on one chip we have to fabricate. So that means you understand 1 billion. 1 billion is the population of India. So that many number of transistors you have to integrate on the same chip. So that means that we should have technology so that these have to be designed, they'll interact with each other. So all of those things will not be possible if we are integrating all these transistors manually. Because automation is there, that's why we are able to achieve this much amount of productivity and this much amount of complexity. Okay, so now let's answer more important question, that why we are doing this particular module. So all of us understand the importance of digital system, and from the survey I understand that most of you have a good background in digital system design. So because most of you have finished your second year of or those who are undergrad, they have at least finished the second year. Some you are in third year, and all the masters and PhD students, they are all from electronics background, so they have done at least a basic course in digital design. So why this particular module? What is the focus? Why? What do we want to do? So because digital system is important and they're getting complex, and this digital system is so important that this would be key of success in the coming decade. You see, there were 4 industrial revolutions. Initially in 1700 or 18th century, there was an industrial revolution. Because of that, Europe became a superpower. And after that, there was another industrial revolution, which because of the steam engines and all. So because this power has generated automatically. And now recently in early 21st century, so we have this internet revolution. And now in the 4th revolution, this machine learning and AI based systems. So here we are in the 4th industrial revolution, which will again change the landscape. And this landscape can be changed only if we have a good, efficient digital system. And that is why, because the focus on digital system is so much, that we should learn how to design such a system, so that we can also contribute ourselves in this 4th industrial revolution. Now, why in this particular module, what do you expect? So because it's only 10 hours and we have a lot of content, so I'll try to be focused. So what I will try to do is I'll not reinvent or basically teach you what a digital, how to all the concepts of digital systems like K-map or Q-Lexi methods. No, this is not what is the goal of this particular course. So, but we still need to revise a couple of these concepts. The other important aspect is we will try to learn how to design digital system. So learn to design is the most important thing. So when we have to learn how to design, so that means we'll start from specification, we'll see that how to interpret those specifications, and we'll try to bifurcate or basically put it into different pieces. You'll see that how we can break things into smaller components and how we can design those smaller components. Okay, and in parallel, we'll also be doing a hardware description language, Verilog particularly. We'll introduce Verilog and we'll try to do some hands-on practice. Okay, so here the approach which will take slightly different here is that will not take will not do this traditional Verilog course where people will where you will start with as a language. You will see what is the syntax, and after that you will go from each syntax and each construct. No, so the way we'll try to do is we'll try to learn the language the way we learn usually the languages. So we'll try to build, try to first read, try to understand how it do, and try to do it by using it. So if you will contribute to the course, so basically you will also do all these hands-on exercises yourself. Then you will see that your understanding of Verilog is much better, because nothing can beat by learning yourself by doing things. So that's how this approach would be hands-on practice. So every time we'll try to write some code, and then from there on we'll try to learn the language. So from there, we'll start picking the syntax one by one. And once we have this way, we'll also have substantial vocabulary of Verilog, and also we'll know that how popular syntax will work, and then we can add on. So as and when required, we'll keep on adding more and more syntax to our vocabulary. So this was my first part. If you have any questions, then I can take it up. You can type in chat box if you have any question. If there is no question, then I'll start for the second module.